A special case of thinking about interference and superpositions is looking at beats. What happens when we get waves which interfere with each other, which are close in frequency but not exactly the same? So just as a quick recap, remember the superposition of waves can be described as a linear superposition of the two, as in we simply add together the contributions from each of the component waves. And this principle of superposition means that we can add any wave together and we will see the result of being the sums of the amplitudes. That principle of superposition is simply saying that the amplitude we observe due to multiple waves at any point is the sum of the individual amplitudes of all the waves which make it up. And that gives rise to different shaped waveforms that we see here. We're now going to consider what happens when we have waves with a common amplitude but with a different frequency. These two waves have a very slightly different frequency, and that superposition, as we say, now appears to have a very slightly changing amplitude. This effect, however, is more pronounced at higher frequencies. So if we look at what happens as we shorten the frequency of each of these component waves, we see that we get a much more exaggerated fluctuation in the amplitude. And what we see is this regular shape seemingly appear, where we have a growth in the amplitude and a shrink, a growth and then a shrink. So for convenience, let's just consider two waves with a common phase difference. That is, they're both starting at 0 at time 0. So they have a common phase difference, delta equals 0. Let's consider the displacement at the position x equals 0. So we have an expression for our first wave and our second wave. They both have a common amplitude, remember, y0. And we have this slightly different frequency, omega 1 and omega 2. From the half angle identity we've used previously, we can find the superposition expressed in this form here. Let's look a bit closer at the superposition. There is an alternate representation that we can use, whereby we say that omega 1 minus omega 2 is simply the difference in the angular frequency of the wave. Omega 1 plus omega 2 over 2 is simply the average omega. So what we have here is we end up with a wave expression where we have a slowly varying amplitude on the wave with time, and we combine that with a wave of average frequency. So what we see here, the result, is that we see the frequency of the wave, the peaks here that we look at, that will have a frequency which is in between the frequencies of the originating waves, while the amplitude varies with time according to the difference in the frequencies. So this delta omega and the omega average become important when we start to consider these interference patterns. What we see is the frequency of the resultant, as we say, is the average of the two input waves, while the amplitude itself oscillates with that frequency delta omega. This is a phenomenon we call beating, and it's what we observe when we're particularly looking at frequencies which are very close together. We will hear a pulsing sound as that amplitude fades in and out. Fundamentally, the closer the frequencies, the smaller delta omega is, so the slower the amplitude oscillation becomes. So if we have very, very close frequencies, we'll see a much slower beat frequency than if we had very, very different angular frequencies. Let's look at an overview of the beats. We say that the oscillation, this omega average, so the high frequency waveform that we observe in this graph, is contained in an envelope with the frequency delta omega over 2. What that means is that this envelope here, the dotted red line, is containing and shaping the amplitude that we observe. We've seen this phenomenon before when we looked at damped oscillations. We looked at the amplitude of the damped oscillation decayed with a decreasing exponential form. That exponential created an envelope which contained the plot of position versus time for that oscillation. In this case, it's much the same. We now have an envelope which is described by that cosine term. But what we notice fundamentally is that the beat frequency is twice the envelope frequency. So where we have the waveform constrained by this envelope, we see that we have peaks in the higher frequency coinciding with the extremes of motion of the envelope. So we get an extreme amplitude twice for every cycle of that envelope. That beat frequency is the difference in frequency between the sources. So if the envelope is delta omega by 2, the beat frequency is delta omega. Let's look at an example. So a double bass can be tuned by matching harmonics. So the fourth harmonic on one string is equal to the third harmonic on the next. The fourth harmonic on the A string is measured at 220 Hz. The third harmonic on the D string is then played. This beat waveform has a frequency of 223 Hz. So calculate the beat frequency, the fundamental first harmonic frequency on the D string. Pause the video and we'll revisit it when we come back. Okay, let's summarize the information. So the third harmonic on the A string is at 220 Hz and the beat waveform has a frequency of 223 Hz. So the first thing we want to think about is what the beat frequency might be. So remember that the intensity of the beat is equal to delta omega. So we're looking at the difference in omega. So remember that the frequency of the beat waveform is equal to the average frequency between the two. A quick bit of rearranging says that the average frequency should be the frequency of the third harmonic on the A string plus the fourth harmonic on the D string over 2. Rearrange this, we get the frequency of the fourth harmonic on the D string is twice the average minus the frequency of the third harmonic on the A string. Now these expressions are expressed in terms of angular frequency, but because there's a 2π scalar on the angular frequency to convert to a real frequency, we can simply convert straight to a direct frequency of f. So the fourth harmonic frequency on the D string must then be 446 Hz minus 220 Hz, which is 226 Hz. That then allows us to calculate the beat frequency as the difference between the two frequencies. So we have 226 minus 220, which gives us the beating frequency at 6 Hz. Let's now think of what the fundamental frequency of the D string is. Remember, we calculate that the fourth harmonic of the D string is at 226 Hz, and we're working in a situation where there's a standing wave. That standing wave, remember, we have our first, second, third harmonic, and the frequency of the harmonic scales with the number of the harmonic. So in this case, to find the first harmonic frequency, we would divide the fourth harmonic frequency by 4. 226 over 4 gives us a fundamental frequency of 56.5 Hz. In summary, whenever we see a beating structure like this, it arises from a difference in frequency between two sources. The resultant waveform that we see is the mean of the constituent frequencies. So this blue curve here has a frequency which is equal to the average of the two constituent frequencies. The beat intensity itself varies with the difference in frequency, delta omega, and that envelope frequency, which constrains the resultant waveform of the two sources, is half that of the beat intensity. So we double the frequency of the beats relative to the envelope. And we can also say that the same relationships apply for absolute frequencies in Hertz because we have that constant 2π scalar between the angular frequency and the absolute frequency.